ನಮಸ್ಕಾರ ಗೆಳೆಯರೆ, ಇವತ್ತು ನಾನು ನಿಮಗೆ ಮಾಡ್ತಿರೋ ಅಂತಹ ಒಂದು ಪೋರ್ಷನ್ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ರಿಲೇಟೆಡ್ ಟು ದ VTU ಸಿಲೆಬಸ್. ಓಕೆ, ಆಸ್ ಪರ್ ದ VTU ಮಾಡೆಲ್ ಪ್ರಕಾರ, ಓಕೆ, VTU ರೋಸ್ಟರ್ ಮಾಡೆಲ್ ಏನಿದೆ ಅಲ್ವಾ, VTU ಮಾಡೆಲ್ ಪ್ರಕಾರ ನಾನೇನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ, ನಿಮಗೆ ಮಾಡೆಲ್ ಕ್ವಶನ್ ಪೇಪರ್ಸ್ನ ಸಾಲ್ವ್ ಮಾಡಿಸ್ತೇನೆ. ಫಸ್ಟ್ ನಾನು ತೊಗೊಂಡಿರೋ ಅಂತ ಒಂದು ಸಬ್ಜೆಕ್ಟ್ ಬಂದ್ಬಿಟ್ಟು DDCO ಅಂತ ಏನು ಕರಿತೀರಾ, DDCO. ಓಕೆ, ಡಿಜಿಟಲ್ ಡಿಸೈನ್ ಆ್ಯಂಡ್ ಕಂಪ್ಯೂಟರ್ ಆರ್ಗನೈಸೇಷನ್. ಕಂಪ್ಲೀಟ್ ಸೊಲ್ಯೂಷನ್ ಆಫ್ VTU ಕೊಟ್ಟಿರೋ ಅಂಥ ಒಂದು ಮಾಡೆಲ್ ಕ್ವಶನ್ ಪೇಪರ್. ಅದು ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ ಕಂಪ್ಲೀಟ್ ಕ್ವಶನ್ ಪೇಪರ್ ಮಾಡಿ ಹಾಕ್ತೀನಿ, ಮಾಡೆಲ್ 1. ಇದೇ ಥರ ತುಂಬ ವೇರಿಯಸ್ ಅದರ್ ಸಬ್ಜೆಕ್ಟ್ಸು ಸಹ ಮಾಡ್ತೀನಿ. ಸೊ ಯಾರ್ಯಾರು ನನ್ನ ಚಾನಲ್ನ ಹೊಸದಾಗಿ ನೋಡ್ತಾ ಇದ್ದಾರೆ, ದಯಮಾಡಿ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಸೊ ದಟ್ ನಿಮಗೆ ನಾನು ಹಾಕೋ ಪ್ರತಿ ವಿಡಿಯೋನು ನಿಮಗೆ ಗೊತ್ತಾಗುತ್ತೆ, ಹಾಗೂ ಸೊಲ್ಯೂಷನ್ನ ನಿಮಗೆ ಎಕ್ಸಾಮ್ ಬರೋದ್ರೊಳಗಡೆ ನೀವು ರೆಡಿ ಆಗಿರ್ತೀರ. ಅದೇ ಥರ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲ, ಅದೇ ರಿಲೇಟೆಡ್ ಮತ್ತು ಬೇರೆ ಪ್ರಾಬ್ಲಮ್ಮು ಸಹ ಕೇಳೋ ಚಾನ್ಸಸ್ ಇರುತ್ತೆ, ಅದನ್ನು ಸಹ ನಾನು ಹೇಳ್ಕೊಡ್ತೀನಿ ನಿಮಗೆ. ಓಕೆ, ಸೊ ಲೆಟ್ ಅಸ್ ಬಿಗಿನ್ ಗೈಸ್. ಸೊ ವಿತೌಟ್ ವೇಸ್ಟಿಂಗ್ ಟೈಮ್ ನಾವೇನು ಮಾಡೋಣ, ಪೋರ್ಷನ್ಸ್ನ ಮುಂದುವರಿಸೋಣ. ಓಕೆ, ಸೊ ಮಾಡೆಲ್ ಕ್ವಶನ್ ಪೇಪರಲ್ಲಿ ಫಸ್ಟ್ ಬಂದಿರೋ ಅಂತಹ ಒಂದು ಕ್ವಶನ್ ಪೇಪರ್ ಸೆಟ್ ಈ ಥರ ಇರುತ್ತೆ ನಿಮ್ಮದು. ಓಕೆ, ಈ ಥರ ಇರುತ್ತೆ ಕ್ವಶನ್ ಪೇಪರ್ 1. ಕ್ವಶನ್ ಪೇಪರಲ್ಲಿ ಮಾಡೆಲ್ ಕ್ವಶನ್ ಪೇಪರ್ 2022 ಏನಿದೆ ಅಲ್ಲ, 2022 ಪ್ಯಾಟರ್ನ್ ಆಫ್ ಸಿಲೆಬಸ್, ಬಟ್ 2023ಗೆ ಕೊಟ್ಟಿರೋ ಅಂಥ ನಿಮಗೆ ಒಂದು ಪ್ಯಾಟರ್ನ್ ಆಫ್ ಎಕ್ಸಾಮಿನೇಷನಲ್ಲಿ ಬಂದಿರೋ ಅಂಥ ಒಂದು ಕ್ವಶನ್ ಪೇಪರು ನೋಡಿ. ಮಾಡೆಲಲ್ಲಿ ಹೇಗೆ ಕೇಳ್ತಾ ಇದ್ದಾರೆ ಅಂದರೆ, ಡೆಮಾನ್ಸ್ಟ್ರೇಟ್ ದ ನಾನ್ ಅಸೋಸಿಯೇಟಿವಿಟಿ ಆಫ್ ದ ನಾರ್ ಗೇಟ್. ಒಂದು ನಾರ್ ಗೇಟ್ನ ನಾವು ಇದನ್ನ 5 ಮಾರ್ಕ್ಸ್ ಕೇಳಿದ್ದಾರೆ ಗೈಸ್, 5 ಮಾರ್ಕ್ಸ್. ನೋಡಿ, ನಾರ್ ಗೇಟು ಅಂಡ್ ನ್ಯಾಂಡ್ ಗೇಟ್, ಈ ಎರಡು ಗೇಟ್ನ ನಾವೇನಂತ ಕರಿತೀವಿ, ಯೂನಿವರ್ಸಲ್ ಗೇಟ್ಸ್ ಅಂತ ಕರಿತೀವಿ. ಏನಂತ ಕರಿತೀವಿ, ಯೂನಿವರ್ಸಲ್ ಗೇಟ್ಸ್ ಅಂತ ಕರಿತೀವಿ. ಯಾಕೆ ಯೂನಿವರ್ಸಲ್ ಅಂತ ಕರಿತೀವಿ ಅಂತಂದ್ರೆ, ದೇರ್ ಇಸ್ ಎ ರೀಸನ್ ಬಿಹೈಂಡ್ ಇಟ್. ದ ರೀಸನ್ ಬಿಹೈಂಡ್ ದಿಸ್ calling of the universal gate for only specifically speaking to the NOR gate and NAND gate is, by using this particular gates, by using this NOR gate, you can create AND gate, you can create OR gate, you can create NOT gate also. Means by using NOR gate or else by using NAND gate, you can create all the basic gate operations. Not only basic gate, you can create exclusive OR gate as well as exclusive NOR gate. Means only the number of NOR gates and the NAND gates which you use for creating an AND gate and creating a OR gate and creating NOT gate, creating exclusive OR and creating exclusive NOR gate, it differs. So that is the strong reason why we call this NOR gate as well as the NAND gate as a universal gates. So in all the digital electronics, we strongly believe these logic gates plays a very predominant role in designing all the electronic circuits. All the electronic circuits, whichever you take guys, all the electronic circuits, I mean to tell, like if you want to design a PCB board for creation of op-amp, if you want to design a PCB board for mobile application, if you want to create a PCB board for laptops, motherboards, as well as for the gaming, any kind of electronic devices which you are building it in today's world, all needs a logic gates, because these are the gates which does the operations of the mathematical functions, that is like addition, multiplication. These are the very major applications which are happening here, and complement. So in order to understand the question, they are asking about demonstrate the non-associativity of the NOR gate. Means, why do we call NOR gate as non-associative property? Non-associative property. Why? The only reason is NOR gate as well as NOT gate, both gates. Not only it is a NOR gate. In tomorrow's questionnaire, they can ask you by changing this NOR gate into a NAND gate. The question can change. Only just they can change the gate. Okay, instead of asking NOR gate, they can ask you about the NAND gate as well. Okay, but here How to prove it? How to demonstrate? NOR gate is not associative, but it is a commutative. Do remember, guys, both this NOR gate as well as the NAND gates are not associative, but they are commutative. And we can prove that. I will show you one of the demonstration how we can prove NOR gate as not associative. Not associative. So let us go in detail about how we can prove. See, the question they were asked is demonstrate the non-associativity of the NOR gate. See, NOR gate means you guys know for a two input NOR gate, how do you write? The symbol, the symbol for two input OR gate, you write it like this. See, the symbol will be like this. Just and put an arc and close the symbol like this. And two inputs defined as A and B, and the output is defined as Y. Means I have just declared it as Y, but the function or the expression what we get at the output of the OR gate is additive property, that is called as A plus B. Simple. What does OR operation does? OR operation does the additive or addition operation. OR gate which does OR gate does addition. But this is for two input OR gate. Similarly, for three input OR gate, if you want to design the symbol, just put one more variable. These are called as variables: A variable, B variable, and C variable. But only thing here is you are increasing the number of output operations by increasing the input one variable. This is how you guys have to remember as a very important point. For two input OR gate, the number of operations which you get is A, B if you take it as inputs and output as Y. The output expression is A plus B. If I put a truth table for this particular kind of a two input OR gate, the number of operations you get is as there are only two inputs. If you define it as n, number of inputs, if you declare it as n as 2, 2 power n will be your operations. Will be your operations or output operations. Outputs. How many outputs you can get for 2 input OR gate means you will get 2 square is 4 operations you can get it. 4 operations. How? Just take it as 0, 1, 2, 3 in the decimal format. Okay, in decimal format. In decimal format, if you write it as 0, 1, 2, 3, in binary format, how do you write it? It's as simple as it is, guys. Binary format, you can write it in 2-bit. 0 as 0, 0, and 1 as 0 and 1, and 2 as 1 and 0, and 3 as 1 and 1. You guys can just ask me, sir, how did you write this binary method? Just putting 0, 1, 1, 0, it is more confusing. How to write it? It's a very good question. There is a method to just write the binary values by knowing the decimal number is just simple. Follow the code called 8421 methodology. 8421 coding system. How this coding system arrived is it's simple. Just take 2 power 0 in the LSB side. This is called as LSB. It is the least significant bit side. The right hand side is always the LSB side, and the left hand side is called as MSB, which is called as most significant bit. Okay, guys, I am telling you how to write the binary number of operations like 0, 0, 0, 1, 1, 0, and 1, 1. How did I write it? Okay, you have to consider this 8421 code system. Okay, how did I arrive at this 8421 is just taking LSB, the first starting letter of LSB as 2 power 0, and the second is 2 power 1, and the third is 2 square, and the fourth is 2 power 3. See, when there are two inputs, if you declare the input variables as n, which I already mentioned you guys very clearly, the number of inputs is always declared as n. Okay, if n is 2, then go it for where only n is 0 and 1. Okay, go for only two input operations, 2 bit. You can call it as these are bits, 2-bit system. For 2 bit, you have to consider only these two values. If it is of a 3 bit, you have to consider one more, this means 4 to 1. If you are using 4 bit operations, means there are 4 inputs, then you have to go for 2 power 3. Okay, so now if I tell you very clearly how did I write this 0 0 0 1 1 0 and 1 1, just consider here as decimal values as 0 1 2 and 3. Okay, in order to mention 0, I will put everywhere, means I don't need of any 8421, so I will just declare it as 0 and 0. Okay, if I want to take 1, if I want to write a decimal value 1 in binary format, just put 1 in the place of 1 in the 8421 coding system. Where is the 1 value? It is in the first place, put here 1, and rest all the positions put it as 0. Rest all the position in the sense, now we are taking only first two positions because it is a 2-bit operation. Okay, and for value of 2 in the decimal, how to write it? 2 is there here. If you see here, there is a 2. In the 2 place, you can put it as 1, and the rest you can put it as 0. Similarly, if you want to put 3, you have to add both this 2 plus 1, which becomes 3. So right in the 2 place 1 and in the 1 place also 1. So this is how I arrived at this decimal into binary operation, that is 0 0 0 1 1 0 and 1 1. So the same operation I have to put it here, 0 0 0 1 1 0 and 1 1. Is it clear, guys? If this is clear, for 3 input operations you can take this 4 as well. For 4 input operations you can take this 8 as well. Okay, it's as simple as it is. Just go on adding numbers 4 5 6 7 8 9 10 11 12 13 14 and 15. Until 15 you can write all these 4 operations. Okay, if you add 8 4 2 1, you will get 15 is the maximum number. So that is why the decimal numbers which we can write in the binary format of 8421 code is from starting from 0 until 15 you can write it. If you keep on continuing the same number, see, for writing 4 you have to put in the 4 place as 1 and put rest of the places as 0. To put 5, you have to put in the place of 4 as 1 and in the place of 1 as 1, and then the rest of the positions you have to put it as 0. Similarly, follow the rest of the positions, you can write it, and I believe in you guys. Okay, I will just teach you how to move the shape and you have to drive it to the destination. Okay, but I will give you the concept and the fundamentals, guys. Don't worry about it. Okay, so but now coming towards the question, okay, coming back towards our question, which is asking about to prove the non-associative property of an OR gate. So I was telling you about OR gate operation of the truth table. So to prove that output is A plus B, when the inputs are A and B, the output will be like 0 plus 0 is 0. The output operation is what? A plus B, right? So input is 0 and 0. If you both add it together, you will get 0. 0 plus 1 is 1, and 1 plus 0 is also 1, and 1 plus 1 is also 1, only in the logical addition. Keep it in mind. Only in logical addition, not in the binary addition. Okay, in the binary addition it becomes like 1 plus 1. If you write it as clearly 1 plus 1 as a binary addition, then it becomes 0 with a carry of 1. Okay, but don't make it confusion with respect to this one. Just writing the truth table, just go with the logical addition. 1 plus 1 is 1. Okay, simple, guys. So this is how we write for OR gate. Similarly, for NOR gate, how do you write? I will just erase the right side portion. This right side portion, I will just erase it. And I will write it here. Okay. This was for OR gate. Okay. For NOR gate, what you have to write is A plus B whole bar. Simple. Whole bar in the sense what? Just complement whatever you have got in this OR operation. See, A plus B we already know. Just complementing means putting a bar on the above of OR gate. Nothing but when there is a 0, you have to put it here as 1. When there is 1, you have to put it as 0. When there is a 1, put 0. When there is 1, put 0. Means just put the opposite of whatever the binary value is there. So this is your OR gate operation of the truth table, whereas OR gate operation of respective OR gate. Okay, why did I thought you guys about the truth table of OR and NOR gate is just behind of knowing this truth table, you can understand how the operation of associative property is happening. Okay, this is what I explained about the two input OR gate. Now coming towards the three input OR gate, it is as simple as it is. Just put one more variable as extra. Okay, I will not explain about the truth table again. Just it's simple. You just put it until 7. Okay, until 7 you can put it, and you can draw the truth table of your own. But now coming towards the proving of associative property, we know that what is the associative property. If anybody recall what is associative property, associative property means in the addition or the additive rule, when a plus b plus c is there, first taking for the first two variables into the bracket, E should be equal to the A plus B plus C by taking the other two variables in the bracket in the right hand side. The left hand side and the right hand side, you will take A plus B plus C only, A plus B plus C, but only thing is what you do is the brackets you are going to change. That means you are going to club only these particular two inputs in the first operation and the rest of the two inputs in the RHS side. So when this is proved, when this both of the operations at the left hand side becomes equal to the right hand side, you can call it is associative property. You can call it as associative property, but they are asking us to prove that NOR gate is not associative, means it is not equal to the a plus b plus c, which is not equal to a plus b plus c in the right hand side. Okay guys, how to prove it? So similarly, just for your knowledge purpose, in the multiplication case, it is just a into b into c, but put brackets in the first two letters, and put bracket in the rest of the two letters in the RHS side. Okay, according to the equation, in the first equation of the additive property, we have to prove that NOR gate is not associative. So in order to prove that, given our NOR gate is a plus b plus c is a whole bar. Okay, here it is guys. I already showed you in the OR gate, it is when it is a 3 input OR gate, then it is a plus b plus c. When it is 3 input NOR gate, just put a bar on the OR gate. Okay, why do we put a bar? Because there is a complement at the bubble. There is a bubble in the symbol, so we have to complement it. Okay, we have to put a bar at the NOR gate. Okay, so in order to prove that a plus b plus c whole bar, which is not equals to the fundamental operation, for considering the three inputs NOR gate, we can write in the sign convention as. So there is a sign convention, guys. You have to prove, means you can prove by using sign convention method. How it is for NOR gate? For NOR gate, okay, remember the sign convention we put is the downward arrow. Okay, and similarly for NAND gate, the sign convention we put is the upward arrow. Okay, keep it in mind, guys. It is nothing but we are complementing. Okay, when you put a downward arrow, we are complementing. When you put a upward arrow, that is for NAND gate. Okay, that is also we are complementing, but this is for multiplication. Okay, this is for multiplication and this is for addition. Okay, so hope these points are very clear. We are following the sign convention methodology in order to prove that a downward arrow and b downward arrow should be equals to the, to prove that, okay, to prove that a downward arrow, b downward arrow, and c, or else you can call it as a nor b whole together should be with the NOR gate of c. Okay, nothing but guys, if I put it in the circuit, NOR gate is like this. First, you are putting a NOR gate for A and B, and whatever the output you are getting, and you are taking the input of C, and you are putting one more NOR gate. So this is the meaning of this particular convection. Okay, this is the meaning of this particular convection. So that is where you can prove that A nor B nor C. Okay, so now if I consider the left hand side, okay, left hand side equations, see, this is all the left hand side equation. Okay, this is all the left hand side equation. So first let us go through the left hand side equation. How did I write it? First you are taking A nor B. Okay, that is nothing but A plus B whole bar. Okay, this is for the first gate, A plus B whole bar, and which is the output is again NOR gate with the A plus B whole bar plus of C whole bar. Okay, NOR gate means nothing but we're taking the two inputs and putting a whole bar. So now the input for the second gate, this is the first gate and this is the second gate. For input for the second gate is A plus B whole bar and another is the C. So if you put a NOR gate for these two inputs, then it becomes, this is the first input and second input putting a whole bar. Hope this is very clear, guys, for the first step. Okay, and after this step, what you have to do, by using the De Morgan's first law. Okay, De Morgan's first law, considering this as a one parameter or one term, this as a one term, okay, and this as one term, putting a whole bar, you can convert by using a De Morgan's first law. I will just show it here. De Morgan's, how do you write? De Morgan's first law, you can write it as A plus B whole bar is there, means you can write it as A bar dot B bar. Simple. This is the first law. So that is what I used it here. Considering this as A plus B whole bar, nothing but now you can split it. A bar, A is nothing but A plus B bar. This is A whole bar dot C bar. Okay, I have just splitted this using this De Morgan's first law. I have just applied on this first particular property. Okay, and now if you follow the rules, basic Boolean rules, when there is A is there with a double bar, then you will get the same variable. This is the rule. Okay, rule number one. These are the rule, guys. You have to remember the rules before going to the equations. Okay, or any of the digital circuits, you have to follow the rules. Okay. So when there is a double bar, you can write it as A. Nothing but A plus B whole double bar means you can write it as A plus B, and C bar I am writing it as it is. Now, if you consider just a multiplication operation with A into C bar as one parameter and B plus of B into C bar as the another operation. Okay, this is the left hand side what we have got it. Okay. Now, if you see in the right hand side, what is there? Right hand side. See what I have done? I have done only the difference is I have put the bracket as a different. See, I have not put the bracket in the A nor B. I have put bracket for B and C. Okay, B and C in the sense for this the circuit will be like A and B and C is having a NOR gate. This is a B, this is C and this is A. B and C is having a NOR gate and the output is given to the another NOR gate and then there is another NOR gate. See, A is in NOR gate with both put together. So both put together is in the sense B and C is having one NOR gate. And the output of this particular function is B plus C whole bar, and here is A. When these both are put together, it will become like a B plus C bar plus of C whole bar. This is what we have written in the downward function. Okay. Oh, sorry, this is A. Okay. This is what we have written in the downward function. Okay, I have just wrote A in the first and B plus C in the second. So you can interchange, nothing problem. But whole bar should be there. Okay, I have just interchanged these two things. Okay, A plus B plus C whole bar, whole bar. Okay, B plus C bar and whole bar. Now splitting this using the same fundamental of De Morgan's first law. Consider this as one term and this as another term. A plus B whole bar nothing but A bar dot B bar is nothing but B is a B plus A whole bar is a B and put a bar on above using the same De Morgan's first law. Now when there is a B double bar or B plus C double bar, you can write it as B plus C and A bar. Now if you multiply A bar into B is the one parameter and A bar into C will be the another parameter. So this shows that, see, AC bar is here, but here you see there is a bar C which is not equal, and there is a BC bar, but here there is B into A bar, means which is not at all equation, not at all equal together, which is not equal, which is not equal. Means LHS side is not equal to the RHS side. So hence you can say that, hence you can prove that the NOR gate is not a associative property, but it proves the commutative. But for commutative I have not yet proved, but you can write it down for a best representation in the examination. Okay, we can now say strongly that the NOR gate is not a associative property, not following or not obeys, not following or not obey the associative property, but it obeys as commutative property, guys. Okay, this is how you have to prove about when they ask you about how to demonstrate an NOR gate is not associative. This is the way how you have to explain it, guys. I hope this is very clear with you guys about the explanation and the concept and the steps what I have explained. Hope these things has made your doubts are very clear. And if you have any doubts, please do comment in the comment box so that I will take it in the next session as a doubt session. Okay. And see you in the next session, guys. Whoever is watching my channel for the first time, please do subscribe so that it will be an encouragement for me as well as to my team members who are behind your success. Okay, who are working behind your success. And from our side, the main request to you guys is, please do work out on whatever the topics we are teaching, and please do work out on the concepts which are very much needed in the engineering concept and the field area. Okay, and and the rest of the things are very clear. And if you have any doubts, please do put in the comment box so that I can look into it, and I will come back to you guys with a better and best solution and with the smart methods. Hope things are clear, guys. Please do share this video with all your friends and your colleagues or else your classmates with the other branches as well, so that they can learn something which they have not learned in the classes. Okay, thank you guys, and wish you all the best for the VTU examination, and all my dear students wish you good day. Okay, thanks for watching my video. See you in the next session.